This is week 1, tutorial 2. I'll be going through question 2, question 3 as well as question 4. Now let's look at question 2 here. We are given the specifications of the diode with a forward voltage of 0.7 volts as well as the forward dissipation rating PD max of 500 milliwatts. Assuming practical diode model, for the following calculations, we need to find what is the values for I1, I2 as well as ID2, and also to calculate the power dissipation of diode D2 here, and explain briefly whether the diode D2 is working properly or not. Looking at this circuit here in figure Q2, we need to first find out if diode D1 as well as D2 are forward or reverse bias. So the way to analyze is this way here. From the positive terminal of the voltage supply Vs, the current will actually travel in a clockwise direction, passing through the resistor R1 first, and then after it passes through resistor R1, it will actually be split up into currents ID2 as well as I2. So the current ID2 will actually go through the positive terminal of D2 first. So therefore, the diode D2 is actually forward bias. Now after passing through the diode D2, this current ID2 here as well as the current I2 will then combine at this junction here, right, to give you back this current which is I1. Okay, so the current I1 will actually enter from the positive terminal of D1. Okay, and hence we can see that since the current enters from the positive terminal of diode D1, so diode D1 will also be forward bias. Okay, so since we know that diode D1 and D2 are both forward bias, so we have to redraw the circuit of figure Q2 to its equivalent circuit. And this is how it will actually look like. This is for diode D2 here. It's been replaced by a battery with a value of 0.7 volts. And right across the diode D2 is actually the resistor R2, which is in parallel with it, and having a current I2 passing through this resistor R2. So the diode D1, which is over here, this is diode D1, will also be replaced by battery, which is 0.7 volts in value. Okay, and voltage source Vs has a value of 10 volts. And current coming out from it is actually current I1. Current going into diode D2 is ID2. Okay, so this is the equivalent circuit here that we have just drawn. Now, so we can actually use this equivalent circuit to calculate for the currents of I1 first. Okay, so our current I1 is here, right? It's passing through the resistor R1. So to calculate for this current I1, we actually can make use of KVL. Now, how we use KVL is we apply KVL around this loop here. Okay, so this loop here will consist of the voltage source Vs, the resistor R1, right, voltage source Vs, resistor R1, as well as the diode D2 and diode D1. So by KVL, this is part A, by KVL, right, we derive the KVL equation around that loop. So we have Vs. Vs is actually the voltage source that provides voltage to resistor R1, the diodes D1 as well as D2. So Vs will be equals to the voltage across R1 plus the voltage across the diode D2 as well as the voltage across the diode D1. So with this, then we can actually input the values of each of the parameters there. So Vs has a value of 10 volts. VR1 can be expanded to give you I1 multiplied by R1. VD2 as well as VD1 will have a voltage of 0.7 volts since they are forward bias. So with this, then we can actually rearrange the equation to give you IR1 times I1R1 is equals to 10 volts minus 1.4 volts. The 1.4 volts is actually a sum of the two 0.7 volts here. And this results in 8.6 volts. So to calculate for the current of I1, we simply divide 8.6 volts divided by the resistance value of R1, which is 75 ohms. So with this, we can calculate I1 to be equals to 115 milliamps. Next, we go on to calculate I2. So this is the current I2 that we are supposed to calculate here. To calculate this current I2, right, as I said before, the voltage across the resistor R2 is actually in parallel, is actually the same as the voltage across the diode D2 here, okay, because we can say that VR2, right, is equals to VD2, okay, because R2 is actually in parallel with diode D2. Okay, so because of this, therefore the voltage of VR2 is actually equals to 0.7 volts. And because of this, to calculate the current of I2, right, VR2 is actually equals to I2R2. Okay, and this happens to be equals to 0.7 volts. So therefore I2, to calculate I2, it's actually equals to 0.7 volts divided by the resistance of R2. Okay, so this will give us 0.7 volts over 100 ohms. Okay, and in this case, the value of I2 will be equals to 7 milliamps. Okay. Next, we proceed to find what is the current of ID2. Okay, so to find the current of ID2, we place a point at here, right? This will be called as point A. Okay, so it's actually this point here. This is point A. Okay, so at point A, right? We can do a KCL at point A. Okay, by KCL, so you will actually have the total current, which is I1, being equals to ID2 added to this I2 here. Okay, so in this case, if you want to find the current of ID2, you simply rearrange the formula to give you I1 minus I2. Okay, so this is actually 115 milliamps minus 7 milliamps. Okay, and the resultant current will be equals to 108 milliamps. On to part B. Okay, so for part B, we are supposed to calculate the power dissipation of diode D2. Okay, so I just put it as PD2 here. So to calculate for this power across the diode D2, we need two parameters, which is actually the voltage across the diode itself, VD2, right, multiplied by the current of ID2, which is the current passing through the diode D2. So in this case here, since the diode D2 is actually forward biased, it has a fault voltage of 0.7 volts. Okay, the current passing through the diode D2 is actually 108 milliamps. So multiplying this will give us an answer of equals to 75.6 milliwatts. Okay, and since we are asked to briefly explain whether the diode is working properly or not, okay, we can see that we are given this PD max rating here. Okay, so using that PD max rating, we can conclude that since, okay, PD2, right, is less than PD max, okay, so therefore diode D2 is still working properly. Okay, so this is for question 2. I'll proceed next to question 3. Okay, in this question 3 here, the diode circuit in this figure Q3A has square input signals as shown in figure Q3B. And what is given for this question here is that the maximum average forward current rating or I naught is 200 milliamps for the diode D1, and its VRRM rating for the diode is also given as 50 volts. Now, for this part of the question here, right, all references are with respect to this timing here. T is equals to 1 second. Now, at this timing here, we are supposed to state the biasing condition of the diode D1. Okay, so at 1 second, right, this is at 1 second here, right, you can see that if you project upwards at 1 second, the voltage across the voltage source Vs, right, will be 5 volts. Okay, so for this reason here, right, we are supposed to change this Vs here, right, to this form here. Okay, plus minus Vs, this is equals to plus 5 volts. So we can actually redraw the figure Q3A to be like this here. Now, I can tell you first that this diode D1 here will be forward bias. Okay, I'll explain later. So I just draw the equivalent model of this diode D1, right, with a battery of 0.7 volts. This is Rs, 43 ohms here. This is Vs, which has a value of plus 5 volts. Now, how do I know that this diode D1 here is actually a forward bias? Right, it's because the current that comes up from the positive terminal of Vs, right, this current here, Is, right, will be coming to this junction here, right, so it will be split up into two currents, ID, as well as the current IL here. Okay, so since the current ID is actually entering from the positive terminal of the diode itself, so that's why the diode D1 is actually forward bias, and hence is replaced by a battery of value 0.7 volts. Okay, so from this equivalent circuit here, right, we should proceed to calculate what is V naught here and the rest of the questions. So let me just put down here, right, D1 is forward bias. Okay, so that's to answer the first part of the question. Now then, next we want to calculate what is V naught here, right? So this is where V naught is, and if you look carefully, this V naught is actually in parallel with this RL here, the resistance RL. So I can just put down here, right, V naught, right, will be equals to VRL, right, as well as equals to VD1. Okay, since V naught and the resistance RL and the diode D1, they are all in parallel. Okay, so therefore V naught will have a value of 0.7 volts. And to calculate for the current Is, okay, Is is the current that comes out from the voltage source Vs. Okay, so we can actually do a KVL in this loop here. Okay, so by creating a KVL equation around the first loop there, right, so we have this equation by KVL. Okay, so Vs will be equals to Vrs plus Vd1. Okay, now Vs, we have already known that this is actually equals to 5 volts. The Vrs here is actually Is times Rs, and Vd1, right, is actually 0.7 volts. Okay, so through here, then we can actually rearrange again to find out what is Is. Is is simply 5 minus 0.7 volts divided by the value of Rs. So in this case, Rs is 43 ohms. Okay, and hence we get a value of Is, which is equals to 100 milliamps. Okay, next we want to calculate what is the current through the load resistor RL, IL. Okay, so over here, we already know that VRL is equals to 0.7 volts. Okay, so VRL by itself, right, is actually IL times RL. Okay, and it has a value of 0.7 volts. Okay, IL is the one that we need to find out, so IL will be equals to 0.7 volts divided by the resistance value of RL here. So in this case, RL has a resistance value of 100 ohms, and therefore we will have a final value of IL being equals to 7 milliamps. Next, to find the current through the diode ID, right? So we actually have to name this point here, right, as point A. Okay, or I put it here. This is point A here. Okay, this is also point A. Point A. Okay, so by KCL, right, at point A, okay, so you'll be able to derive the equation of IS being equals to ID plus IL. Okay, and from here we can calculate or rearrange the equation to give you ID is equals to IS minus IL. So IS just now we have already calculated is equals to 100 milliamps, and IL here is 7 milliamps. So therefore ID will be 93 milliamps. To know whether the diode D1 is actually functioning properly, and to give a reason, right? Notice that at the beginning of this question here, right, we are given this maximum average forward current rating of the diode, which is equals to 200 milliamps. So since we have already calculated the current that's passing through the diode D1, right, as 93 milliamps here, right? So therefore we can put this reason here, since ID, right, is less than I naught. Okay, so since this ID here is actually 93 milliamps, and the I naught, right, or the maximum average forward current rating is 200 milliamps. Okay, so therefore the diode D1 is still functioning properly. Okay, so that's for question 3 here. Next, I'm going to repeat for this question 4 here. So we are supposed to repeat question 3 for time of 3 seconds. At a time of 3 seconds, which is here, right, as you can see, the voltage Vs will be equals to -5. Okay, and first thing is we need to find out whether the diode D1 here, is it forward or reverse bias. So if it's Vs is -5 here, right, we can imagine that this Vs here is being replaced by this battery here, which is inverted. Okay, and it's running at -5 volts. Okay, so we can actually redraw the circuit here, right. You can actually straight away see that the diode D1, right, with the arrangement of the battery in reverse like this here, right, the diode D1 will actually be reverse bias. Okay, so that's why I'll be replacing this diode D1 here, right, since I know from first look that it's going to be reverse bias by an open switch. Okay. Next, I'll be calculating what is the voltage V0 here, right? So the voltage V0, as you can see, is still in parallel with the resistance RL. Okay, so therefore V0 is actually equals to VRL. Okay, And if you look carefully, right, what we have in this circuit here is actually a series circuit. Okay, let me just highlight to you. Okay, the diode D1 is actually a open switch, so when you remove that, okay, since no current is actually passing through the open switch, right, you can see that what we have is actually a series circuit, right, that has current flowing this way here, okay, passing through the resistor RL, and then of course through RS as well. Okay, so and we also see that this V0 here, right, the output voltage is actually in parallel with this resistor RL here. Okay, so to calculate what is the voltage across the resistor RL, right, since we have a series circuit here, right, so therefore we can actually calculate VRL using voltage divider rule. Okay, so in this case, voltage across RL here will be equals to RL over RS plus RL multiplied by the Vs. Okay, so in this case, RL here is 100 ohms over 43 plus 100 ohms multiplied by Vs. In this case, Vs is minus 5 volts. Okay, so if you calculate this out, VRL will be equals to minus 3.5 volts. Next, we are going to calculate what is the current of IS as well as IL. Okay, so since IS is this way here, okay, it's in the same direction as IL here, right? So that means both are actually having the same value. Okay, so we have IS is actually equals to IL. Okay, so to calculate this current, both currents here, IS as well as IL, right? Notice that we can actually take Vs, okay, to divide this with RS plus RL, since it's a series circuit. Okay, and Vs is actually minus 5, RS is 43 ohms, and RL is 100 ohms. Okay, so you take minus 5 volts divided by a total of 143 ohms, so you will actually get a value of minus 34.97 milliamps. Okay, and then talking about the current passing through the diode ID, right? So I just put back the current here. So this is current ID trying to pass through the diode D1, which is reverse bias. As you can see, since it's open circuit, right, so that means the current passing through this diode D1 here will actually be equals to 0 amps. Okay, then we are supposed to find out whether this diode here, right, is still functioning properly or not. Okay, now remember that the question also gives you the VRM value of 50 volts. Okay, so I just put down here VRM given is 50 volts. Okay, so we need to find out in this case here what is the voltage across the diode itself here. Okay, so that means what is VD1. Okay, so VD1, right, will be in parallel with this voltage VRL here. Okay, and just now we have already calculated VRL is actually minus 3.5 volts. Okay, through here. Okay, so therefore we can conclude that since VD1 is less than VRRM, okay, now take note, this VRM here, right, no doubt is given in 50 volts here, okay, but it's actually a negative value. Okay, so in this case we should disregard the negative sign here. Okay, so VD1, right, in reverse will be 3.5 volts. Okay, VRM here is 50 volts. Okay, so therefore D1 is still working properly. Okay, and part B, we are supposed to sketch the voltage waveform of V0 with respect to the input waveform in figure Q3b here. Okay, so I will simply draw V0, right, against time. Okay, so this timing here is in terms of seconds, right? So we have the timing of 1 second, 2 seconds, 3, as well as 4 seconds. Okay, now for the first 2 seconds, right, as you can see from Vs, it's always constant 5 volts. Okay, so when Vs is 5 volts, the voltage across the diode D1 will actually be 0.7. That means this diode D1 here, right, will be 0.7 volts. Okay, you can also see that because V0 is actually in parallel with the diode D1, so that's why it's always 0.7 volts. Okay, when the voltage source is plus 5 volts for the first 2 seconds. The next 2 seconds, right, the voltage Vs, the next 2 seconds, from 2 seconds to 4 seconds, the voltage Vs is actually minus 5 volts. Okay, so it's always a constant minus 5 volts there. When the voltage source is minus 5 volts, right, again, since V0 is actually in parallel with the diode D1, so we have already calculated just now, right, the output voltage V0 is actually minus 3.5. So you have to cater for this point here at minus 3.5 volts. Okay, so this minus 3.5 volts will be seen at the output voltage V0 from 2 to 4 seconds, and then you just have to join up these 2 points here. Okay, so that's actually the sketch of the voltage waveform V0, right, from 0 seconds to 4 seconds. And this is all for week 1 tutorial 2.